one of the things I want to do with Keone on a regular basis is to sit down with him and teach him. He's obviously a student of wanting to learn how to build things in the shop, and that has worked out really nicely. And so I started thinking about what would I tell him. Well, why don't I tell him how a wind turbine makes electricity from the wind, and go through all of those steps. And then I thought, well, that's a pretty interesting subject. Maybe more people would like to hear it, so opened up the invitation, so we're all here. And I've done a little bit of research over the last couple of days and come up with some more. I learned a few things. But where I'd like to start is I'd like to explain to you where did air come from? And so why don't we start at the beginning? About 14 billion years ago, a bunch of people got together and decided we needed a universe. Call them gods, I guess. And so for about 10 billion years, it took before our solar system was created. So our sun first, and then the planets, and then our moon. And the story about the moon is very interesting. A large planetoid object collided with the Earth and caused quite a bit of stuff, debris, to get shed. And it did a couple things. One is it created enough debris for the moon to be formed about 200,000 miles away from the Earth, which is 93 million miles from the sun. And it also tilted the Earth, so its north and south axis were a little bit askew. And that's important because as we rotate around the sun, if we're tilted, there are times when the north is closer to the sun and the angle is better, and there are times when you're on the opposite side, and so that causes the seasons: summer, winter, spring, and fall. If not for that, and if not for the moon, which causes gravitational force every time we rotate, we wouldn't have the tides, and we wouldn't have the seasons, and we wouldn't be here. So, cool. The other thing that really happened to an amazing fortune for us is that the Earth, there are 9 planets, and we're the third from the suns. The ones that are closer to the sun are too hot, and the ones that are further away are too cold. And so they call it the Goldilocks Orbit, and we're in that and have been for about 5 billion years. We've been rotating in the same orbit at the same distance from the sun, and our average temperature over that period of time has been about 60 degrees. If you know that water freezes at 32 and it boils at 212, that's only 180 degrees, and that's a very narrow temperature range. And for us to coexist, or to year after millions of years after billions of years, stay in an orbit where the temperature is averaging 60 degrees, if not for that, we wouldn't be here. So 5 billion years ago, the sun is formed, then the Earth, then the moon, and then a little while after that, water. And water exists on the surface of the, we're basically a cold rock until enough hydrogen was gases from the solar spaces around us was brought to us by meteors and asteroids, and we were just massively bombarded over billions of years. And here came the oxygen, and here came the hydrogen, and those two combined, and it made moisture in the air, which rained on the Earth and made the oceans, the rivers, and the lakes. And so we're referred to as the blue planet. Out of all, we've never found another blue planet anywhere. So that makes us unique, and it's all because we're in this Goldilocks orbit. So a lot of reasons for us to really appreciate the fact that we're here at all. So we have water, and then we had enough oxygen, and there was enough nitrogen that was either came from the minerals or came from outer space, and oxygen and nitrogen. I didn't know this until the last couple of days, but air that we breathe is 20% oxygen, 80% nitrogen. Okay, that's cool. And so now we have water, we have air, and then we have plants, then we have simple animals, and then we have human beings. So about 100,000 years ago, this line right here is when upright animals known as human beings were walking on the face of the earth. They weren't intelligent, but they were walking. So here you are, all of this time, 14 billion years, and the first human is here, and the first intelligent human is here, and we start using energy here, and the population growth happens here. So we have zero population and zero use of fossil fuels until right here. I can't draw the line skinny enough to represent the time that humans have been on the face of the earth, but it's right here. And this is what the curve looks like. Zero, boom, 8 billion people, and the use of fossil fuels for about the last 200 years. And so when people talk to you about climate warming and they refer to natural cycle, I suggest you remind them that the last couple hundred years has been like no other cycle ever in the history of the 14 billion years the universe has been around. So I say, debunk that. The other thing I found out when I was doing my, how am I gonna explain how a wind turbine works to Keone, is I thought I would measure the amount of air that goes through our turbine. And I was blown away. I was really blown away. Our rotor is...
Literally. Yeah, no pun
I didn't think you'd get that. Our rotor is 7 meters, and when you square that and multiply it times 0.7854, you come up with 38 meters squared is the disk area. Now, we have a limit on how big we can make the rotor because it has to fit on a machine that fits inside of a 20-foot container. So that's as big as we can get, and unless we go to a bigger container or don't put it in one. Other people make more power simply by making their rotors bigger, and they don't care about efficiency, but we do care about efficiency. So I'll get back to that, I'll talk about efficiency in a minute, but if we are 38 meters square, this is looking at the side of the rotor, and we're 1 meter deep, every second we're flowing 38 cubic meters every second for every meter per second. So if we're at 10 meters per second, we're flowing 380 cubic meters. So this table is about 2 cubic meters. If you look at, this is a meter, that's a meter, and this is a meter, that's a cubic meter. And that weighs 1.3 kilograms, which is 2.2 pounds, or about almost 3 pounds, almost 3 pounds for every cubic meter. So, and then that's per second. Per minute, it's this. Per hour, it's that. Times this 1.3 is the weight of the air, which is this many kilograms per hour, times pounds in a kilogram. 4 million pounds of air is flowing through our turbine every hour when it's making full power. 4 million pounds. I was blown away. Okay, and then the other thing I studied was how many revolutions does this thing make and how much power does it make? And I find that every revolution makes about 1 watt of power. Only a watt of power. Here are all these big 5 blades spinning at this high speed and this strong wind, but we're only making 1 watt per revolution. But lots of revolutions, and it all adds up. Which really points to one thing to me anyway, and that is, it's incumbent upon us, it's important to us, it is critical to us that every revolution, the shape of the blade is very efficient, and that the parasitic losses on the machine are very low. That means friction and drag. So everything we've done is to reduce the parasitics and improve the efficiency so that we can get a lot of power out of a rotor that has a limit to how big it can be. So here's a pictorial of the mast looking down on it, the propeller shaft, the hub, and a blade sticking out, and looking at the blade from the top down. And so the blade has foil shape. This part of the foil is longer than this part, and it's where it's big, it's 16 degrees from flat, and where it's small, it's almost 0 degrees of pitch. So that's called twist. Here comes the wind. The wind is always coming in this direction, but the wind is pushing on this side, and the wind is going around the nose and traveling along the back side, and then all of this wind and that wind join right here in a big scrambled mess. But because the distance across the backside is longer, because of the curvature, then the air that goes across the bottom is denser than the air across the top, which causes high pressure on this side, low pressure on that side. And the blade can go only in one direction. It can't go in the direction of the push, so it skates and escapes in that clockwise direction. Here is a little example of a skating force. So, first of all, before I show you the skating force, this has potential energy, and it's just hanging there. Potential energy just became kinetic energy, okay? The two are equal. One is waiting to go somewhere, and one is going somewhere. So motion is what, so when we talk about kinetic energy in our wind, it's because the wind is moving. And based on how big the rotor is, based on the density of the wind, and based how fast it's traveling, we have a formula to determine what the kinetic energy is. And then we learn from experience how much power we get from the machine. And if the machine is making 100 kilowatt, if the air has 100 kilowatts of power in it, and our machine is making 48 kilowatts of power, we're 48% efficient. That's the simplicity of that. So here is an example of a skating force. If I push down on this, it doesn't go anywhere. If I push on the side, it doesn't go anywhere. If I push on the end, it moves, obviously, because it's easy. But what if I push on a somewhat of an angle, and it doesn't slide that way, it doesn't slide that way, it slides this way, so that's a skating force. And that's what's making our turbine turn, is this force is on an angle, and this lift is on an angle, and there's only one direction it can go, that's clockwise, that's called a skating force. Might be interested in knowing that water weighs 766 times as much as air for the same volume. I've just about covered everything I thought I needed to. Do you have any?
Well, so I think our dad's done an excellent job of covering the background and how wind energy works.
Well, I wanted to talk about the alternator and how it made electricity.
Please.
Do you want me to?
Yeah, go ahead.
Okay. All right, so we have an alternator, and it's a very excellent alternator. It is designed to be very powerful and very efficient. And basically you have a stator, and it has wound copper coils. There's 48 of them. And it has a rotor inside of it, turns, and it has magnets that are attached to the rotor face. and there's 54 of those. There's a different number of magnets than there are coils, so that only one magnet lines up with one coil, and all the rest of them are somewhat not aligned. And that makes it easier for us to get the thing started, because magnets want to stick. And so if they all stuck, if there were 48 magnets and 48 coils, it'd really be hard to get us started. The other thing is that the air gap between the magnet and the coil is very small. Our alternator is rated at 10 kilowatts, yet it can take massive amounts of short-term inrush of current, so that it is many times more powerful than 10 kW for short periods of time, which works very nicely when we have a gust of wind coming along and we want to control the RPM of the rotor. We just let the alternator make more power for a short amount of time to stop the thing from overspeeding. Don't know how much further to go with that, except that as the magnets are traveling past the coils, it breaks lines of flux, which is a force that, and it generates a voltage. For every RPM, we get about 0.6 of a volt, and we turn at about almost 600 RPM, so we make almost 660 volts. And it's a variable RPM, so it's a variable frequency, and it's a variable voltage machine, but it's very efficient. It's 98% efficient. That means we only lose 2% in friction and heat. That's a high number, and that's a great number. And and with our electronics and the programming, our computer is adjusting the load on this a couple hundred times a second to control the RPM of the propeller. The propeller is always turning at a tip speed ratio somewhere around 6:1. So the propeller is turning at 120 RPM, miles per hour, excuse me, and the wind going into it is only 20 miles an hour, 6:1. So we maintain that, but the computer doesn't care what the ratio is. It cares whether it can make more power or it's losing power. And it adjusts the load on the alternator 200 times a second to maintain the perfect load, so we maintain the perfect tip speed ratio. That's our dancing with the wind that we do, and it's special. Nobody else does it.
Per second?
Per second.
What's the ideal wind speed to be optimized?
There is none. There's nothing for me to be able to tell you that 15.6 miles an hour is the optimum speed. It works all the way from here to there.
So that is kind of a good segue into some of the principles behind us and the dancing with the wind. And so very, very early on in this project, when we were looking at building a portable wind turbine and knowing that we had practical limitations with how big we could make the machine, how can we maximize the energy density of this portable wind turbine? How can we take this form factor that we have and have it produce as much energy as possible? Well, understanding that the energy in wind, it grows exponentially at the cube relationship of wind speed. It's not linear transition, it's exponential. So if you go from a 10 mile an hour wind to a 20 mile an hour wind, there's not double the energy in the 20, there's 8 times. 2 times 2 times 2. Right. I mean, just simply going from a 10 to a 12 mile an hour wind, there's almost twice as much energy in that 12 as there is in a 10. So the energy in wind grows quickly. Small increases in wind speed equal big increases in kinetic energy. How do you take advantage of that? Well, you maintain this tip speed ratio with how fast the rotor is turning versus how fast the wind is blowing. There's always an optimum relationship. And so that's what our computer programming does, is it maintains that perfect relationship. And 6-to-1 is something that will come out of the textbook, but the reality is that environmental conditions change. And so whether you're at sea level or 6,000 feet elevation, you're gonna have very different air density at those two elevations. If it's raining out, if the blades have gotten dirty over time, all of that is gonna affect performance. Humidity is gonna affect it. But that is the beauty of our programming, is it doesn't care. It doesn't care. It's always looking to make the most power that it possibly can. Here's one way of thinking about how our Dancing with the Wind system works. So in these electric vehicles that are driving around on the road right now, you press on the brake and it charges the battery. Regenerative braking. And that's essentially what we're doing with our wind turbine. We're feathering the brake so that we make as much power as we possibly can without bringing it to a stop. So it doesn't care about air density, it doesn't care about environmental conditions, it doesn't care about blade condition, it optimizes for the highest power output. That is unique, that is proprietary, and that is decidedly different than the way that the rest of the wind turbines in the world work. And so, this kind of comes down to a background as to why what we're building out there is hands down the most technologically advanced small wind turbine there is. Hard stop, not even close. We're so far out in front of anything else that's happening, it's not even close. And we're portable, which is unique. It's a game changer, that in itself. And so the portability aspect of the machine, it's common for people to see that and think, oh, that's great, temporary power, portable power, great. Sure, that is one of the applications of our portability, but I think that because of this superior performance that I'm talking about, many of our wind turbines are gonna be installed in one location and they're gonna stay there for their life. So how does portability benefit that? From the initial setup. So the difference there is a traditional wind turbine that goes into the ground, that gets put in this spot right here, and it's gonna be there for the entirety of its life. I mean, before an owner is gonna make the investment to put the wind turbine there, they wanna make sure that the wind conditions in that location are gonna justify the wind turbine for the life of the machine. So it's most likely that person's gonna do an 18-month wind study. They're just gonna measure the wind conditions at that one spot for 1.5 years to make sure that throughout the seasons, there's enough average wind to make that investment worth it. Then, assuming you get through that 18-month period and you go, okay, I've got something here, it's another 6 months to do your site improvements, to install the wind turbine, to get your permits, to make the connections and all that. That's 2+ years to set up a traditional wind turbine that doesn't have the performance that we do. So our system, on the other hand, we don't need a wind study. And one, because it's not permanent in its installation. Another is our superior low wind speed performance and the fact that we make power in those lower wind conditions that other machines can't. So you can wheel ours in and power in an hour. And if you like that spot, great. If you think to yourself, hey, you know what, maybe it might be better over there on the other side of the barn, a couple hours you're there. You're not permanent. You're not married to any one location. And some areas are going to have seasonal weather changes. It's good wind in the summer over here and good in the winter over here. You can move. You can follow that. To
And you can service.
To back up a little bit though, with this blade that we have, so this is the bottom 5 feet of our blade. Here is the foil section that is drawn here. This design is the product of modeling over 2 million unique blades before we selected this shape right here. And that is how we achieved the very high performance that we get out of this blade. 48% coefficient of power. That is more than double the incumbent technology. So we have this very powerful blade that is intentionally built very light, so it has low inertia, so that when a gust of wind comes along or the wind speed changes, this rotor wants to take off. And then that's where our programming and these adjustments that happen a couple hundred times a second really come into play. And that's how we dance with the wind and take advantage of the exponential power that is available in wind gusts. And so, now, there are a lot of very unique features here. I mean, every aspect of this wind turbine has been analyzed in excruciating detail with a couple of primary objectives. One, how can we extract the highest percentage of kinetic energy that passes over the wind turbine rotor and convert that into electricity, energy capture. And then once we capture that energy, how can we deliver the highest percentage of that captured energy to the user, minimizing the parasitic losses in the system. And so those two things have been paramount in the entire design process. And of course, safety, ease of operation, knowing that these wind turbines are going to be going into remote areas all around the world, and that they're going to be operated by, most likely untrained workforce. And so the machine needs to be intuitive in its operation. It needs to be easy to operate. So those have been some of the primary design considerations. Now, in order for us to make a portable wind turbine that does all of this stuff, that's easy to operate and we can get it anywhere in the world easily, well, we've designed this system to fit into a shipping container. And so, as you all know, our wind turbine folds down, folds up, and into its own trailer, and that's what fits into the shipping container. So the fact that our mast lays down, well, it's a requirement for the portability aspect. But there's two other benefits of that. One benefit is that when you're in the field and anytime you need to service the wind turbine, all your service work is done right here. You never have to climb way up there to the top of the wind turbine. Something that we know, we're acutely aware of the challenges of doing that with our background in this field services business. And so being able to do all your service work here at ground level is a big deal. And the other thing, and that's a big deal about that, is storm avoidance, storm protection. Traditional wind turbines that are put in the ground and they don't lay down, they all are designed to withstand that 100-year storm that could potentially damage the wind turbine. And so knowing that they will occasionally have to withstand these horrendous storms, the wind turbines are overbuilt. They're made very robust. And in doing so, it compromises the performance of the wind turbine in order to make them so robust. Our system, on the other hand, we were able to just focus on performance through and through from start to finish, knowing that should that storm present itself, simply lay down, and that's how we protect the wind turbine. So, big deal in itself. So, you you're probably starting to get the flavor of how all of these unique features kind of intermingle with one another to create the most technologically advanced small wind turbine there is anywhere in the world that also happens to be portable.
Yeah.
Very good, John. Hey, was that exactly half hour or close to it?
I think we got 30 seconds.
Yeah.
Yeah.
Right.
All right.
Any questions?
All right, back to work.
All right.
All right.
Thanks,
Thank
guys.
you. Thank
Hope
you
you
all.
enjoyed it.